Ladies and gentlemen, thank you for coming. I would like to present some information and some solution of my work on Institute for Metal Forming on field materials characterization and using of Mathematica, especially CUDA, link to develop some new solvers for nonlinear equations, which I use to explain some phenomena in material science, like diffusion, temperature field, or deformation, which is mostly nonlinear. It's not elastic, it's everything plastic. Okay. First of all, where is Institute of Metal Forming in Germany? Near to Dresden and Leipzig. It's a small city, something like 30,000 people and 5,000 students. So we are really small according to the another cities. Our institute have 5 groups, working groups, teams, which one of those I'm head. We work together to describe materials and build new models to describe some processes, production processes, or also to generate some models for controlling, very fast controlling controller. In this case, we will concentrate on multiscaling modeling. Maybe someone from you have heard about it. This is some idea which we start from atom scale and going on to the something like here, crashing test and also simulation. For that, we need mostly very deep knowledge about material. Our group concentrate on this field. Here we leave this field to the physics, and we work together with physics, and they give us some models to describe some phenomena like I don't know, slip effects and so on. If we go to the topic using of Mathematica, as you see, we use Mathematica to describe or also take all data together into the some models and transfer this to the fast control systems or industrial scale processes. We work on process and material optimization as well as development of new technology and new materials. Those technology must be cheap, first of all, and good to environment and so on. Sorry. Okay. What we use to solve our system, as we know all for material science or engineering construction, mostly is used FAM method, which give us a very smooth expression of some phenomena. I use here finite difference method to describe all of those phenomena because it was simply to implement into the GPU calculation. So I will show you everything about it. So we started first of all about concepts. I don't know what's happened. Sorry. First of all, in Mathematica, mostly function used CPU to solve some problems. We can use 2 different ways to do this. First of all, we can use serial processing or parallel processing. It's very simple to implement, or in function compile. Using compile, we can parallel parallelize this or use another function like parallel evaluation or parallel table and so on. We can use it, and here are the transport data between RAM data and CPU. That's mostly the problem of some codes, because using RAM transport between CPU or RAM, we have large lag of time. We have small speed of data transfer. Mostly, I don't know, sorry, but I don't know what's happened. Mostly ideas of colleagues. Can you get it a little bit?
Is it clips?
Yeah. A little bit.
Yeah, sure.
Okay. Can you put it a little bit lower? Okay. So we use mostly in codes of commercial software this data transfer from RAM to a video RAM on GPU, and then compute it and return data. And this is large lag if we have a large data set. I think 1,000, 10,000 or something like that. It's the boundary of this. If we use only video RAM, it goes perfect. I will show you by a little bit. Maybe I'm nervous. Okay, here's some example of using different concepts of those combinations. So first of all, you see here we have large data table, 300 to 300. We solve this in kernel of Mathematica, and we have this time here. If we go to the compilation with, for example, C, we get faster. So we can take this into the account that if we compile this function, we will much faster. Of course, we can use also a method with list table and parallelization. We get a little bit faster because this function is very simple, and the compiler choose also something in compilation time. If we get a function in CUDA, like here, it's the same, a little bit complicated, because we need to take into the account indexing and so on. So we use this. We calculated this in double precision, and this we can compute with two different ways. First of all, we can do this in combination 3, where we transport the data from RAM to RAM and from back. If we get this compilation only one time, something with me, sorry. Maybe I will. I think that's the problem. Okay, good. Okay, if we do not use transport, the time will be also now reduced. So the data will live on GPU system. So that's the perfect way. Not every system computation concept use this, and there is more complicated systems like FEM need transport this data. So that's the problem. In FDM method, we don't need it, so we computed everything on our system. So that's the time. As you can see, for example, Mathematica kernel, if we take grid size in millions, it's not enough Scala for this. And if we take the combination 3, which we transport the data between CPU and GPU, it takes a lot of time, and that's the difference. And mostly there is the problem to speed up. If you have some function, we use GPU speed up and it doesn't happen. That's the problem here. If you get only one time to the CUDA, to the GPU, and then solve the system in CUDA, that's your speed up potential which you can use. So that's most problem of systems which are custom for commercial using and so on. So that's most problematic thing. Okay, we go now to some idea what happens in CUDA. I had implemented this whole system in homogeneous matrix, but homogeneous structure. But I work now to develop more complicated shapes. It's also not problem because we can solve this system in domain and shoot it through the CUDA and then make some computation between those tables. Okay, now the idea of my code is using only VRAM, put it everything into the kernel, compute with using shared memory. It's very slow, very small, but very fast. You have here the speed of this shared memory. If we use it internal in kernel, we have pretty good results for the speed up. Here's some example. We use this solver for Bitonic. I had wrote some Bitonic sorter for CUDA with pretty large grid size. For example, by 1 million points or integer double precision points, we get something like 1 second to sort everything. So it's worked pretty well. And also I need to tell about Titan X. We have here 2 different graphic cards. One is my own, and the second one was donated by NVIDIA. And you can get here some difference between those two, because one of them is 6 GB VRAM, and the another is 12. So the capacity is double. Okay. In my software, I use it, or software function set, I use it some of those, or all of those equation. We have here PD for motion, for stress deviators, which are depend from motion. We have stiffness matrix, everything, diffusion between cells, temperature diffusion, and so heat diffusion, and so on. So basically, very complicated system, which is not linear and must be carefully solved. Okay, because I work with large data, I have every time problem with saving of the sets of data. So I use Paralia solving, evaluation for one trend, one process make me this calculation with CUDA, and another move the data to the hard disk. I measured the time between this set, and until the data are moved, I break, move to the RAM new data set, start one more time the next set of calculations. So I don't have lack of saving the data in the process. So it's very comfortable. You can go to home and everything will be also saved. If you have system complication, you can take the data one more time and return to your calculations. So each data will be move it to the hard drive. Okay, if we build some function, we have now a problem with compilation because, sorry, we don't know how large should be our block. Block size is very important, and also register size. If we make some optimization on this, like here, for example, to calculation of volume on 1 million elements, you can see here's the function which I use to compile the data. I can set here maximum register which are used per trend. And this gives me results with very different speedups. That means if we compile, we need also to see what kind of graphic card we use because we have some lag every time and depends how large is our block to how many register we use. It's something like depend from our bandwidth between GPU and VRAM. If we can optimize it through different block size, we get maximum what is for us in this perfect. Here, if we don't use this large shared memory and so on, and only generate, as you can see, we have 700 to 3 cubic grid size, so it's very large. And also we can generate some it's quasi random generator. It's also from a little bit changed for 3D generation. I think in data of Mathematica, you can find this random generator. I have a little bit changed it for 3D. In this case, in Mathematica case work, this only 1D. In 3D, it's work also fine. Yeah. If we get the optimization about the size of block, we can also speed up this about 50%. So it's not so big, but even there, if we have 1 week, 1 day, it's already something. Okay, what we can do with this new, maybe not new system, this idea. We can calculate diffusion. This is some system like 2 different phases in steel, for example. We have austenite, which have high solution of carbon. And we have ferrite, which is very low solution. So by diffusion calculation, we will see movement of atoms from ferrite to austenite. And we have 2 different diffusion coefficients, which we can here also apply this. If we get it, we get something like this, results. You can see some points. It's pretty not so good resolution because it was calculated in 4K. It was reduced to HD. So some points are, pixels are not so pretty well. It's you see some problems with calculation. If we want to get some stress calculation in this system, we can do this, and I can show you now this calculation results. The volume of ferrite is a little bit higher than austenite, so ferrite want to get out of this and deform elastic or plastic austenite. So you can see stress field. You can see some plastic deformation where the stress is going down. That's the relaxation of plastic movement of some hexahedron. Okay, if we use for this model for deformation, we can use some like this model. It's a little bit complicated if you, it's something like how much I need to press to move some piece or some hexahedron in this case. So we declare this in this equation. That's give us nonlinearity of equation, and here some results. Because this matrix is also this pieces was also with Voronoi Voronoi method generated with different texture of grinds. In material, you get different slip line of material in this case. So with 1,000 elements, you get already pretty cool results for calculation, and also you get information for construction, how much you can deform or how much you can put it some force on some pieces. Okay, now I'm ready with presentation. I would like to show you some codes and some movies, which we can also generate from this. I have little bit I had little bit problems with generate of some graphics and movies because everything was generated in Mathematica graphic 3D. So if I put it there, millions of elements, it's become to problems. But after 1 week, I had some movies. So this is not this. Here, for example, this computation of this last one. This is slip effects, which you can also see by deformation in reality. And those effects we observed also in our facilities, experiment facilities. We can also generate different grind size, which were here calculated. And also we can see here this, it's a little bit slow because we have many frames here. You can see also the diffusion or change of concentration between ferrite and austenite, which I already explained this. It's taking a little bit time. Now you see everything what happens after this. It's really good simulation because we observed in microscope the same condition of carbon concentration in ferrite and carbon concentration in austenite. Okay, here simulation of deformation. I didn't get the cross section. This is 12 million elements which were simulated simultaneously on 4 cards, 4 graphic cards, because the system can make simulation of 4 different scenarios. It's really interesting to see what's happened here. For example, compression test with 12 million elements. And here, for example, the tensile test of some piece of steel. Okay, now I will show you some code. Because the code is a little bit, it's not only text, because this text is interact with my ideas, which I can,
In those movies, what are the dimensions, like roughly?
18 millimeters. So something like, I don't know, half an inch, something like that. A little bit smaller. Or larger. I don't know. The grinds are large in this case because this is the electrical steel with very large grind size. Okay, you can see here very simple code, only text, which is then compiled with this function. Its work, each function work with double precision. So in this case, it's pretty good. We generate here homogeneous matrix, homogeneous grid of the system, and this grid will be deformed before we start the calculation, some sample geometry and so on. So first of all will homogeneous homogeneous grid generated, and then this deformed to the numerically to the final start position. Final start position. Okay, now a little bit complicated because the CUDA code is really basic programming. I use it Mathematica to generate the script of algorithm. To generate, you can see here, for example, some eight nodes, which I calculate the vectors of strain or volume in this case, and then implement this to the real code. The real code which we use is a little bit lower. In this case here, this is the loading to the shared memory. And the real code you can see here ahead of the code. Here is shared memory, and here you get a little bit. And here is the calculation of the volume simply. If we implement this, if we use the string operators, we get whole C code for our computation, which we need. So if you want something to change, you can go to the scripts, change something, and will be automatically changed in your code later. Okay, here's the solution computation of volume, for example, of hexahedron. Yeah. Here we have also for computation for stress. It's also something like in this, something like this, and we get also after operation of strings, like here, string join, replace, and so on, whole large script to compiling. So, thank you very much for your attention.